All right, welcome to This Explainer. Today, we're diving straight into what is arguably the ultimate cosmic detective story. We're going to look at exactly how humanity managed to pull off the literal impossible and actually photograph the darkest, most elusive monsters in our universe, black holes.
Okay, but before we figure out how to snap a picture of one, we really need to understand what we're dealing with here. So let's just start with the wildest question possible. What actually happens to you if you fall into one of these gravitational monsters?
Well, it's not a fun ride. Just imagine falling in. To anyone watching you from the outside, they'd see your perception of time completely slow down until you seem to just freeze, turn red, and eventually visually disappear. But for you, gravity becomes so insanely concentrated that your body is literally stretched out. Your cells get torn apart into a hot stream of plasma just one atom wide. It's a pretty terrifying process that physicists affectionately call spaghettification.
So, moving on to Section 1, Monsters of the Cosmos, Understanding the Extremes of the Universe.
Just how big do these monsters actually get? Well, the largest known supermassive black hole we've found so far, it's designated S50014+81, has an entirely incomprehensible mass of 40 billion times that of our own sun. We're talking about a cosmic titan that has just been feeding for billions of years. But here's the massive visual roadblock we hit. Black holes don't reflect anything. What you're actually looking for out there in space is the event horizon. This is the absolute point of no return. You cross this boundary, and even light itself is permanently trapped. So you are essentially trying to photograph a sphere of pure darkness. Which brings us right to Section 2. Photographing the invisible, the impossible problem of capturing a black hole. So how exactly do you capture a shadow that's cast against glowing plasma? Computer scientist Dr. Katie Bauman hit the nail on the head when she described the sheer scale of this challenge. To capture the supermassive black hole in the M87 galaxy, which is 55 million light-years away, by the way, we would be looking for a target that appears to us the exact same size as an orange sitting on the surface of the moon. Let's look at Section 3, the Earth-sized telescope, connecting the world's observatories. To zoom in on an orange on the moon, a single telescope simply is not going to cut it. Mathematically, we would need a satellite dish the size of the entire planet. Enter the Event Horizon Telescope, or EHT. By taking 8 completely independent radio observatories scattered all across the globe and synchronizing them perfectly, astronomers effectively hacked together a single, Earth-sized virtual telescope. But there's a catch here, and it was brilliantly explained by Dr. Bowman. Since we obviously can't cover the whole Earth in mirrors, collecting data from just these 8 scattered sites is kind of like turning the Earth into a spinning disco ball that's missing most of its reflective pieces. You get data, sure, but it leaves these enormous visual gaps that desperately need to be filled in. So the really crucial step here was the algorithm they used to fill in those gaps. Scientists didn't just tell a computer, hey, find a black hole, because that would bias the result to only show exactly what we expected to see. Instead, they fed the algorithm puzzle pieces of everyday images. We're talking cats, dogs, buildings, trees, and told it to connect the data using those. The idea being, if everyday images can reconstruct a black hole ring, we can be highly confident that human bias didn't just invent the shape. Section 4, the first historic snapshots, bringing the shadows into the light. And you know what? That completely ingenious method actually paid off. In April 2019, the world literally stopped. The EHT unveiled the very first image of a black hole in the M87 galaxy. Humanity finally saw it, that iconic, bright, asymmetrical ring of superheated plasma circling a deep, dark central shadow. But they absolutely didn't stop there. Let's compare that distant behemoth to Sagittarius A star, which is the supermassive black hole right at the center of our very own Milky Way. M87 is a colossal 6.5 billion solar masses, but it's really far away. Sagittarius A star is right in our cosmic backyard, but it's vastly smaller, just 4 million solar masses. Because it's so much smaller, the gas swirls around it incredibly fast, making it extremely hard to capture without blurring. Yet, against all odds, the EHT managed to release its image in 2022. Moving to Section 5, Sharpening the Shadows, Pushing the Boundaries of Resolution and Physics. Getting those first snapshots was an incredible triumph, for sure. But the scientific process, it's never finished. In recent years, researchers have been constantly upgrading our view. We're going to look at 2 massive advancements here, the Primo machine learning algorithm and the use of ALMA polarimetry. Let's break down Primo first. The team basically trained a computer on 30,000 highly accurate simulations of gas accreting into a black hole. By doing this, Primo essentially learned the optimal way to fill in the missing gaps of our Earth-sized disco ball. And the result? It drastically sharpened the M87 image, literally slashing the width of that bright ring in half, giving us unprecedented resolution to test the very laws of gravity itself.
The second major update was utilizing polarized light. Just like how your polarized sunglasses filter out specific light waves, astronomers filter the data from M87, definitively proving that the bright ring is fiercely magnetized. This is huge because it finally solves a major mystery. These strong magnetic fields are what allow a black hole to resist just swallowing everything and instead launch these massive relativistic jets of energetic particles deep into space. Finally, Section 6, the ultimate fate, how a black hole eventually dies. As absolutely indestructible as these astronomical titans seem to be, they don't last forever. They actually slowly evaporate via a completely mind-bending quantum process discovered by Stephen Hawking, appropriately known as Hawking radiation. See, empty space isn't actually empty. Virtual particles pop in and out of existence all the time. When this happens right at the very edge of the event horizon, one particle gets sucked in and the other escapes. Over time, this slowly drains the black hole's mass and energy.
Now, this happens incredibly slowly at first, but as the black hole shrinks, the evaporation accelerates. When it's down to the mass of an asteroid, it radiates heat at room temperature. By the time it shrinks to the mass of a mountain, it's radiating with the intense heat of our sun. And in the final second of its life, it explodes with the phenomenal force of billions of nuclear weapons. But don't hold your breath waiting for it. For the supermassive black holes we photographed today, this process will take roughly 1 Google years. That is a 1 followed by 100 zeros. Over that unimaginably long time span, the rest of the universe will have likely become utterly uninhabitable. So, when the very last black hole detonates in a Google years, leaving behind nothing but empty space, who will be around to witness the universe go permanently dark?